Irrigation, also referred to as watering of plants, is the practice of applying controlled amounts of water to land to help grow crops, landscape plants, and lawns. Irrigation has been a key aspect of agriculture for over 5,000 years and has been developed by many cultures around the world. Irrigation helps to grow crops, maintain landscapes, and revegetate disturbed soils in dry areas and during times of below-average rainfall. In addition to these uses, irrigation is also employed to protect crops from frost, suppress weed growth in grain fields, and prevent soil consolidation. It is also used to cool livestock, reduce dust, dispose of sewage, and support mining operations. Drainage, which involves the removal of surface and subsurface water from a given location, is often studied in conjunction with irrigation. There are several methods of irrigation that differ in how water is supplied to plants. Surface irrigation, also known as gravity irrigation, is the oldest form of irrigation and has been in use for thousands of years. In sprinkler irrigation, water is piped to one or more central locations within the field and distributed by overhead high-pressure water devices. Micro-irrigation is a system that distributes water under low pressure through a piped network and applies it as a small discharge to each plant. Micro-irrigation uses less pressure and water flow than sprinkler irrigation. Drip irrigation delivers water directly to the root zone of plants. Sub-irrigation has been used in field crops in areas with high water tables for many years. It involves artificially raising the water table to moisten the soil below the root zone of plants. Irrigation water can come from groundwater, extracted from springs or by using wells, from surface water, withdrawn from rivers, lakes, or reservoirs, or from non-conventional sources like treated wastewater, desalinated water, drainage water, or fog collection. Irrigation can be supplementary to rainfall, which is common in many parts of the world as rain-fed agriculture, or it can be full irrigation, where crops rarely rely on any contribution from rainfall. Full irrigation is less common and only occurs in arid landscapes with very low rainfall or when crops are grown in semi-arid areas outside of rainy seasons. The environmental effects of irrigation relate to the changes in quantity and quality of soil and water as a result of irrigation and the subsequent effects on natural and social conditions in river basins and downstream of an irrigation scheme. The effects stem from the altered hydrological conditions caused by the installation and operation of the irrigation scheme. Amongst some of these problems is depletion of underground aquifers through overdrafting. Soil can be over-irrigated due to poor distribution uniformity or management wastes water, chemicals, and may lead to water pollution. Over-irrigation can cause deep drainage from rising water tables that can lead to problems of irrigation salinity requiring water table control by some form of subsurface land drainage. In 2000, the total fertile land was 2,788,000 square kilometers, 689 million acres, and it was equipped with irrigation infrastructure worldwide. About 68% of this area is in Asia, 17% in the Americas, 9% in Europe, 5% in Africa and 1% in Oceania. The largest contiguous areas of high irrigation density are found in northern and eastern India and Pakistan along the Ganges and Indus rivers, in the Hai-he, Huanghe, and Yangtze basins in China, along the Nile River in Egypt and Sudan, and in the Mississippi-Missouri River Basin, the southern Great Plains, and in parts of California in the United States. Smaller irrigation areas are spread across almost all populated parts of the world. 2. By 2012, the area of irrigated land had increased to an estimated total of 3,242,917 square kilometers, 801 million acres, which is nearly the size of India. The irrigation of 20% of farming land accounts for the production of 40% of food production. Global overview. The scale of irrigation increased dramatically over the 20th century. In 1800, 8 million hectares globally were irrigated, in 1950, 94 million hectares, and in 1990, 235 million hectares. By 1990, 30% of the global food production came from irrigated land. Irrigation techniques across the globe includes canals redirecting surface water, groundwater pumping, and diverting water from dams. National governments lead most irrigation schemes within their borders, but private investors and other nations, especially the United States, China, and European countries like the United Kingdom, also fund and organize some schemes within other nations. By 2021, the global land area equipped for irrigation reached 352 million ha, an increase of 22% from the 289 million ha of 2000 and more than twice the 1960s land area equipped for irrigation. The vast majority is located in Asia, 70%, where irrigation was a key component of the Green Revolution. The Americas account for 16% and Europe for 8% of the world total. India, 76 million ha, and China, 75 million ha, have the largest equipped area for irrigation, far ahead of the United States of America, 27 million ha. China and India also have the largest net gains in equipped area between 2000 and 2020, plus 21 million ha for China and plus 15 million ha for India. All the regions saw increases in the area equipped for irrigation, with Africa growing the fastest, plus 29%, followed by Asia, plus 25%, Oceania, plus 24%, the Americas, plus 19%, and Europe, plus 2%. Irrigation enables the production of more crops, especially commodity crops in areas which otherwise could not support them. Countries frequently invested in irrigation to increase wheat, rice, or cotton production, often with the overarching goal of increasing self-sufficiency. Example values for crops. Irrigation water can come from groundwater, extracted from springs or by using wells, from surface water, withdrawn from rivers, lakes, or reservoirs, or from non-conventional sources like treated wastewater, desalinated water, drainage water, or fog collection. While floodwater harvesting belongs to the accepted irrigation methods, rainwater harvesting is usually not considered as a form of irrigation. Rainwater harvesting is the collection of runoff water from roofs or unused land and the concentration of this. Irrigation with recycled municipal wastewater can also serve to fertilize plants if it contains nutrients, such as nitrogen, phosphorus, and potassium. There are benefits of using recycled water for irrigation, including the lower cost compared to some other sources and consistency of supply regardless of season, climatic conditions, and associated water restrictions. When reclaimed water is used for irrigation in agriculture, the nutrient, nitrogen and phosphorus, content of the treated wastewater has the benefit of acting as a fertilizer. This can make the reuse of excreta contained in sewage attractive. The irrigation water can be used in different ways on different crops, such as for food crops to be eaten raw or for crops which are intended for human consumption to be eaten raw or unprocessed. For processed food crops, crops which are intended for human consumption not to be eaten raw but after food processing, i.e., cooked, industrially processed. It can also be used on crops which are not intended for human consumption, example pastures, forage, fiber, ornamental, seed, forest and turf crops. In developing countries, agriculture is increasingly using untreated municipal wastewater for irrigation, often in an unsafe manner. Cities provide lucrative markets for fresh produce, so they are attractive to farmers. However, because agriculture has to compete for increasingly scarce water resources with industry and municipal users, there is often no alternative for farmers but to use water polluted with urban waste directly to water their crops. There can be significant health hazards related to using untreated wastewater in agriculture. Municipal wastewater can contain a mixture of chemical and biological pollutants. In low-income countries, there are often high levels of pathogens from excreta. In emerging nations, where industrial development is outpacing environmental regulation, there are increasing risks from inorganic and organic chemicals. The World Health Organization developed guidelines for safe use of wastewater in 2006, advocating a multiple barrier approach wastewater use, for example by encouraging farmers to adopt various risk-reducing behaviors. These include ceasing irrigation a few days before harvesting to allow pathogens to die off in the sunlight, applying water carefully so it does not contaminate leaves likely to be eaten raw, cleaning vegetables with disinfectant, or allowing fecal sludge used in farming to dry before being used as a human manure. Drawbacks or risks often mentioned include the content of potentially harmful substances such as bacteria, heavy metals, or organic pollutants, including pharmaceuticals, personal care products and pesticides. Irrigation with wastewater can have both positive and negative effects on soil and plants, depending on the composition of the wastewater and on the soil or plant characteristics. Irrigation water can also come from non-conventional sources like treated wastewater, desalinated water, drainage water, or fog collection. In countries where humid air sweeps through at night, water can be obtained by condensation onto cold surfaces. This is practiced in the vineyards at Lanzarote using stones to condense water. Fog collectors are also made of canvas or foil sheets. Using condensate from air conditioning units as a water source is also becoming more popular in large urban areas. As of November 2019, a Glasgow-based startup has helped a farmer in Scotland to establish edible salt marsh crops irrigated with seawater. An acre of previously marginal land has been put under cultivation to grow samphire, sea blight, and sea aster. These plants yield a higher profit than potatoes. The land is flood irrigated twice a day to simulate tidal flooding. The water is pumped from the sea using wind power. Additional benefits are soil remediation and carbon sequestration. Until the 1960s, there were fewer than half the number of people on the planet as of 2024. People were not as wealthy as today, consumed fewer calories and ate less meat, so less water was needed to produce their food. They required a third of the volume of water humans presently take from rivers. Today, the competition for water resources is much more intense, because there are now more than 7 billion people on the planet, increasing the likelihood of overconsumption of food produced by water-thirsty animal agriculture and intensive farming practices. This creates increasing competition for water from industry, urbanization, and biofuel crops. Farmers will have to strive to increase productivity to meet growing demands for food, while industry and cities find ways to use water more efficiently. Successful agriculture is dependent upon farmers having sufficient access to water. However, water scarcity is already a critical constraint to farming in many parts of the world. Irrigation methods. There are several methods of irrigation. They vary in how the water is supplied to the plants. The goal is to apply the water to the plants as uniformly as possible, so that each plant has the amount of water it needs, neither too much nor too little. Irrigation can also be understood whether it is supplementary to rainfall, as happens in many parts of the world, or whether it is full irrigation whereby crops rarely depend on any contribution from rainfall. Full irrigation is less common and only happens in arid landscapes experiencing very low rainfall or when crops are grown in semi-arid areas outside of any rainy seasons. Surface irrigation. Surface irrigation, also known as gravity irrigation, is the oldest form of irrigation and has been in use for thousands of years. In surface, furrow, flood, or level basin irrigation systems, water moves across the surface of agricultural lands, in order to wet it and infiltrate into the soil. Water moves by following gravity or the slope of the land. Surface irrigation can be subdivided into furrow, border strip, or basin irrigation. It is often called flood irrigation when the irrigation results in flooding or near flooding of the cultivated land. Historically, surface irrigation is the most common method of irrigating agricultural land across most parts of the world. The water application efficiency of surface irrigation is typically lower than other forms of irrigation, due in part to the lack of control of applied depths. Surface irrigation involves a significantly lower capital cost and energy requirement than pressurized irrigation systems. Hence it is often the irrigation choice for developing nations, for low-value crops and for large fields. Where water levels from the irrigation source permit, the levels are controlled by dikes, levees, usually plugged by soil. This is often seen in terraced rice fields, rice paddies, where the method is used to flood or control the level of water in each distinct field. In some cases, the water is pumped, or lifted by human or animal power to the level of the land. Surface irrigation is even used to water urban gardens in certain areas, for example, in and around Phoenix, Arizona. The irrigated area is surrounded by a berm and the water is delivered according to a schedule set by a local irrigation district. A special form of irrigation using surface water is spate irrigation, also called floodwater harvesting. In case of a flood, spate water is diverted to normally dry river beds, wadis, using a network of dams, gates and channels and spread over large areas. The moisture stored in the soil will be used thereafter to grow crops. Spate irrigation areas are in particular located in semi-arid or arid, mountainous regions. Micro-irrigation, sometimes called localized irrigation, low-volume irrigation, or trickle irrigation is a system where water is distributed under low pressure through a pipe network, in a predetermined pattern, and applied as a small discharge to each plant or adjacent to it. Traditional drip irrigation use individual emitters, subsurface drip irrigation, SDI, microspray or microsprinklers, and mini bubbler irrigation all belong to this category of irrigation methods. Drip irrigation, also known as micro-irrigation or trickle irrigation, functions as its name suggests. In this system, water is delivered at or near the root zone of plants, one drop at a time. This method can be the most water-efficient method of irrigation. If managed properly, evaporation and runoff are minimized. The field water efficiency of drip irrigation is typically in the range of 80 to 90% when managed correctly. In modern agriculture, drip irrigation is often combined with plastic mulch, further reducing evaporation, and is also the means of delivery of fertilizer. The process is known as fertigation. Deep percolation, where water moves below the root zone, can occur if a drip system is operated for too long or if the delivery rate is too high. Drip irrigation methods range from very high-tech and computerized to low-tech and labor-intensive. Lower water pressures are usually needed than for most other types of systems, with the exception of low-energy center pivot systems and surface irrigation systems, and the system can be designed for uniformity throughout a field or for precise water delivery to individual plants in a landscape containing a mix of plant species. Although it is difficult to regulate pressure on steep slopes, pressure compensating emitters are available, so the field does not have to be level. High-tech solutions involve precisely calibrated emitters located along lines of tubing that extend from a computerized set of valves. In sprinkler or overhead irrigation, water is piped to one or more central locations within the field and distributed by overhead high-pressure sprinklers or guns. A system using sprinklers, sprays, or guns mounted overhead on permanently installed risers is often referred to as a solid-set irrigation system. Higher pressure sprinklers that rotate are called rotors and are driven by a ball drive, gear drive, or impact mechanism. Rotors can be designed to rotate in a full or partial circle. Guns are similar to rotors, except that they generally operate at very high pressures of 275 to 900 kPa, 40 to 130 psi, and flows of 3 to 76 L/s, 50 to 1200 US gal/min, usually with nozzle diameters in the range of 10 to 50 mm, 0.5 to 1.9 in. Guns are used not only for irrigation, but also for industrial applications such as dust suppression and logging. Sprinklers can also be mounted on moving platforms connected to the water source by a hose. Automatically moving wheeled systems known as traveling sprinklers may irrigate areas such as small farms, sports fields, parks, pastures, and cemeteries unattended. Most of these use a length of polyethylene tubing wound on a steel drum. As the tubing is wound on the drum powered by the irrigation water or a small gas engine, the sprinkler is pulled across the field. When the sprinkler arrives back at the reel, the system shuts off. This type of system is known to most people as a water reel traveling irrigation sprinkler, and they are used extensively for dust suppression, irrigation, and land application of wastewater. Other travelers use a flat rubber hose that is dragged along behind while the sprinkler platform is pulled by a cable. Center pivot irrigation is a form of sprinkler irrigation utilizing several segments of pipe, usually galvanized steel or aluminum, joined and supported by trusses, mounted on wheeled towers with sprinklers positioned along its length. The system moves in a circular pattern and is fed with water from the pivot point at the center of the arc. These systems are found and used in all parts of the world and allow irrigation of all types of terrain. Newer systems have drop sprinkler heads as shown in the image that follows. As of 2017, most center pivot systems have drops hanging from a U-shaped pipe attached at the top of the pipe with sprinkler heads that are positioned a few feet, at most, above the crop, thus limiting evaporative losses. Drops can also be used with drag hoses or bubblers that deposit the water directly on the ground between crops. Crops are often planted in a circle to conform to the center pivot. This type of system is known as LEPA, Low Energy Precision Application. Originally, most center pivots were water-powered. These were replaced by hydraulic systems, TL irrigation, and electric motor-driven systems, Reinke, Valley, Trimatic. Many modern pivots feature GPS devices. A series of pipes, each with a wheel of about 1.5 m diameter permanently affixed to its midpoint, and sprinklers along its length, are coupled together. Water is supplied at one end using a large hose. After sufficient irrigation has been applied to one strip of the field, the hose is removed, the water drained from the system, and the assembly rolled either by hand or with a purpose-built mechanism, so that the sprinklers are moved to a different position across the field. The hose is reconnected. The process is repeated in a pattern until the whole field has been irrigated. This system is less expensive to install than a center pivot, but much more labor-intensive to operate. It does not travel automatically across the field, it applies water in a stationary strip, must be drained, and then rolled to a new strip. Most systems use 100 or 130 mm, 4 or 5 inch, diameter aluminum pipe. The pipe doubles both as water transport and as an axle for rotating all the wheels. A drive system, often found near the center of the wheel line, rotates the clamped together pipe sections as a single axle, rolling the whole wheel line. Manual adjustment of individual wheel positions may be necessary if the system becomes misaligned. Wheel line systems are limited in the amount of water they can carry, and limited in the height of crops that can be irrigated. One useful feature of a lateral move system is that it consists of sections that can be easily disconnected, adapting to field shape as the line is moved. They are most often used for small, rectilinear, or oddly shaped fields, hilly or mountainous regions, or in regions where labor is inexpensive. A lawn sprinkler system is permanently installed, as opposed to a hose-end sprinkler, which is portable. Sprinkler systems are installed in residential lawns, in commercial landscapes, for churches and schools, in public parks and cemeteries, and on golf courses. Most of the components of these irrigation systems are hidden underground, since aesthetics are important in a landscape. A typical lawn sprinkler system will consist of one or more zones, limited in size by the capacity of the water source. Each zone will cover a designated portion of the landscape. Sections of the landscape will usually be divided by microclimate, type of plant material, and type of irrigation equipment. A landscape irrigation system may also include zones containing drip irrigation, bubblers, or other types of equipment besides sprinklers. Although manual systems are still used, most lawn sprinkler systems may be operated automatically using an irrigation controller, sometimes called a clock or timer. Most automatic systems employ electric solenoid valves. Each zone has one or more of these valves that are wired to the controller. When the controller sends power to the valve opens, allowing water to flow to the sprinklers in that zone. There are two main types of sprinklers used in lawn irrigation: pop-up spray heads and rotors. Spray heads have a fixed spray pattern, while rotors have one or more streams that rotate. Spray heads are used to cover smaller areas, while rotors are used for larger areas. Golf course rotors are sometimes so large that a single sprinkler is combined with a valve and called a valve-in head. When used in a turf area, the sprinklers are installed with the top of the head flush with the ground surface. When the system is pressurized, the head will pop up out of the ground and water the desired area until the valve closes and shuts off that zone. Once there is no more pressure in the lateral line, the sprinkler head will retract back into the ground. In flower beds or shrub areas, sprinklers may be mounted on above-ground risers, or even taller pop-up sprinklers may be used and installed flush as in a lawn area. There are many types of hose-end sprinklers. Many of them are smaller versions of larger agricultural and landscape sprinklers, sized to work with a typical garden hose. Some have a spiked base allowing them to be temporarily stuck in the ground, while others have a sled base designed to be dragged while attached to the hose. Sub-irrigation has been used for many years in field crops in areas with high water tables. It is a method of artificially raising the water table to allow the soil to be moistened from below the plant's root zone. Often those systems are located on permanent grasslands in lowlands or river valleys and combined with drainage infrastructure. A system of pumping stations, canals, weirs, and gates allows it to increase or decrease the water level in a network of ditches and thereby control the water table. Sub-irrigation is also used in the commercial greenhouse production, usually for potted plants. Water is delivered from below, absorbed by upwards, and the excess collected for recycling. Typically, a solution of water and nutrients floods a container or flows through a trough for a short period of time, 10 to 20 minutes, and is then pumped back into a holding tank for reuse. Sub-irrigation in greenhouses requires fairly sophisticated, expensive equipment and management. Advantages are water and nutrient conservation, and labor savings through reduced system maintenance and automation. It is similar in principle and action to subsurface basin irrigation. Another type of sub-irrigation is the self-watering container, also known as a sub-irrigated planter. This consists of a planter suspended over a reservoir with some type of wicking material such as a polyester rope. The water is drawn up the wick through capillary action. A similar technique is the wicking bed. This too uses capillary action. Efficiency. Modern irrigation methods are efficient enough to supply the entire field uniformly with water, so that each plant has the amount of water it needs, neither too much nor too little. Water use efficiency in the field can be determined as follows. Field water efficiency, percent, equals, water transpired by crop divided by water applied to field, x 100. Increased irrigation efficiency has a number of positive outcomes for the farmer, the community, and the wider environment. Low application efficiency infers that the amount of water applied to the field is in excess of the crop or field requirements. Increasing the application efficiency means that the amount of crop produced per unit of water increases. Improved efficiency may either be achieved by applying less water to an existing field or by using water more wisely, thereby achieving higher yields in the same area of land. In some parts of the world, farmers are charged for irrigation water, hence over-application has a direct financial cost to the farmer. Irrigation often requires pumping energy, either electricity or fossil fuel, to deliver water to the field or supply the correct operating pressure. Hence increased efficiency will reduce both the water cost and energy cost per unit of agricultural production. A reduction of water use on one field may mean that the farmer is able to irrigate a larger area of land, increasing total agricultural production. Low efficiency usually means that excess water is lost through seepage or runoff, both of which can result in loss of crop nutrients or pesticides with potential adverse impacts on the surrounding environment. Improving the efficiency of irrigation is usually achieved in one of two ways, either by improving the system design or by optimizing the irrigation management. Improving system design includes conversion from one form of irrigation to another, e.g. from furrow to drip irrigation, and also through small changes in the current system, for example changing flow rates and operating pressures. Irrigation management refers to the scheduling of irrigation events and decisions around how much water is applied. Challenges. Environmental impacts. Negative impacts frequently accompany extensive irrigation. Some projects which diverted surface water for irrigation dried up the water sources, which led to a more extreme regional climate. Projects that relied on groundwater and pumped too much from underground aquifers created subsidence and salinization. Salinization of irrigation water in turn damaged the crops and seeped into drinking water. Pests and pathogens also thrived in the irrigation canals or ponds full of still water, which created regional outbreaks of diseases like malaria and schistosomiasis. Governments also used irrigation schemes to encourage migration, especially of more desirable populations into an area. Additionally, some of these large nationwide schemes failed to pay off at all, costing more than any benefit gained from increased crop yields. Overdrafting, depletion, of underground aquifers. In the mid-20th century, the advent of diesel and electric motors led to systems that could pump groundwater out of major aquifers faster than drainage basins could refill them. This can lead to permanent loss of aquifer capacity, decreased water quality, ground subsidence, and other problems. The future of food production in such areas as the North China Plain, the Punjab region in India and Pakistan, and the Great Plains of the US is threatened by this phenomenon. The environmental impact of irrigation relate to the changes in quantity and quality of soil and water as a result of irrigation and the subsequent effects on natural and social conditions in river basins and downstream of an irrigation scheme. The effects stem from the altered hydrological conditions caused by the installation and operation of the irrigation scheme. Amongst some of these problems is depletion of underground aquifers through overdrafting. Soil can be over-irrigated due to poor distribution uniformity or management wastes water, chemicals, and may lead to water pollution. Over-irrigation can cause deep drainage from rising water tables that can lead to problems of irrigation salinity requiring water-table control by some form of subsurface land drainage. However, if the soil is under-irrigated, it gives poor soil salinity control, which leads to increased soil salinity with the consequent buildup of toxic salts on the soil surface in areas with high evaporation. This requires either leaching to remove these salts and a method of drainage to carry the salts away. Irrigation with saline or high sodium water may damage soil structure owing to the formation of alkaline soil. Technical challenges. Over-irrigation because of poor distribution uniformity in the furrows. Potato plants were oppressed and turned yellow. Irrigation schemes involve solving numerous engineering and economic problems while minimizing negative environmental consequences. Such problems include ground subsidence, e.g. New Orleans, Louisiana. Under-irrigation or irrigation giving only just enough water for the plant, e.g. in drip line irrigation, gives poor soil salinity control, which leads to increased soil salinity with consequent buildup of toxic salts on soil surface in areas with high evaporation. This requires either leaching to remove these salts and a method of drainage to carry the salts away. When using drip lines, the leaching is best done regularly at certain intervals, with only a slight excess of water, so that the salt is flushed back under the plant's roots. Over-irrigation because of poor distribution uniformity or management wastes water, chemicals, and may lead to water pollution. Deep drainage, from over-irrigation, may result in rising water tables, which in some instances will lead to problems of irrigation salinity requiring water-table control by some form of subsurface land drainage. For example, in Australia, over-abstraction of fresh water for intensive irrigation activities has caused 33% of the land area to be at risk of salination. Drainage front instability, also known as viscous fingering, where an unstable drainage front results in a pattern of fingers and viscous entrapped saturated zones. Irrigation with saline or high sodium water may damage soil structure owing to the formation of alkaline soil. Clogging of filters, algae can clog filters, drip installations, and nozzles. Chlorination, algaecide, UV, and ultrasonic methods can be used for algae control in irrigation systems. Complications in accurately measuring irrigation performance, which changes over time and space using measures such as productivity, efficiency, equity, and adequacy. Macro irrigation, typical in intensive agriculture, where also are used agrochemicals, often causes eutrophication. Social aspects. Competition for surface water rights and territory defense. Assisting smallholders in sustainably and collectively managing irrigation technology and changes in technology. Thank you for watching this video.